In section 5.2, we are going to talk about the definite integral. In section 5.0, we talked about the indefinite integral. Now for the indefinite integral, notice we have no limits of integration. There are no numbers here. So all we can do here is find the antiderivative, and again, we have no limits of integration. Now the definite integral is f of x, the integral of f of x dx, but it's over the interval a to b. So it's between two different x values. Now, what does that represent? Let's say that this is function f of x, and this is a, this is b, which are the limits of integration. Then the integral of f of x dx between a and b, it represents the area under the curve between a and b. That's what the integral represents. Okay, so once again, the integral may represent the area between the x values of a and b and under the curve f of x dx, but above the x-axis. Okay, so here's the definition of the definite integral. So this section is going to talk about the definite integral, whereas 5.0 talked about the indefinite integral. And once again, indefinite integral has no limits of integration, whereas the definite integral does. So if f of x is non-negative and f of x is defined on the interval a to b, then the integral of f of x dx from a to b is the area below the function and above the x-axis on that interval. Okay, so if this is the function f of x, then the integral represents the area between a and b, so in other words, the shaded area. Now, what if f of x is negative or below the x-axis on the interval? Well, in that case, we're going to say, so let's say this is a, let's say this is b, then the integral of f of x dx from a to b is the area above the x-axis minus the area below the x-axis. So we would have to subtract these two areas, and we'll see some examples a little later on. So the main thing I want you guys to know is anytime we have the integral of f of x dx from a to b, this represents area under the curve f of x between a and b. So integral, the definite integral, represents area. That's what I want you guys to get from this. So here's an example. We are given this function square root of 2 squared minus x squared dx, and we want to know the integral from of this function between -2 and 2. These are called the limits of integration. So here are limits of integration sorry for the bad writing. The limits of integration are -2 and 2. Okay, so we basically want to find the area under this curve between -2 and 2. So we can notice that if you go to desmos.com and you would graph this function square root of 2 squared minus x squared dx, right? And notice that this is a semicircle, it's half of a circle. And we also know that the area of a circle is given by pi times r squared. So for this semicircle, the radius is 2. So if we wanted to find the area of this entire circle, that'll be pi times r squared, because the radius is 2. Put this into a calculator, we get 12.5663706. But then we want to divide this by 2 because we just want the area of the semicircle, not the whole circle, and that'll be 6.2832 units, square units. Area is always in square units. So we did a calculus problem, but just by looking at the area of a circle and dividing it by 2. But what I want you to know is that this integral does represent the area under the curve and above the x-axis. Here's another example. We want to find the area of the absolute value of 4x minus 2 dx between 0 and 4. So first thing we're going to do is we're going to go to desmos.com and we're going to graph this. So I'm going to graph the absolute value of 4x minus 2. And when you want to limit the graph just to an interval, so in this case the interval is between 0 and 4, you put the squiggly brackets and we're going to put 0 less than or equal to x less than or equal to 4 to get that graph. Now we want to find the area under this curve and above the x-axis. So this graph is split up into two different triangles, as we can see. So let's find the area of both triangles. Notice that this is 0 to 1. So this point here, where the two triangles are split up, that point's going to be a half. It's the halfway point between 0 and 1. Now we also know that the area of a triangle is given by the formula 1/2 times base times height. So the base of this is going to be 1/2. It's again the distance from 0 to a half, and the height is 2. So if I find the area of that blue triangle, it'll be 1/2 times the base, which is 1/2, times the height, which is 2, and that gives you just 1/2. Okay, now what about the big triangle? So for the big triangle, the base is 3.5 and the height is 14. So the area is going to be 1/2 times 3.5 times 14, which is 24.5. And then if we add these two together, the total area will be 0.5, which is a half. That's the area of the first triangle, plus 24.5, which will give you 25. So if we're looking for the area geometrically, which is what we did in this example and the one previous to it, then we want to graph these shapes, and we just want to find the area of these shapes using geometry, geometrical formulas. All right, next example, we want to find the area that is given here. So this like shaded blue part. Now, first of all, this area is represented by this integral, because remember the integral represents area under a curve and above the x-axis. So we first want to know what are our limits of integration, what are a and b. Well, we were looking at the x values between 1 and 2. So a is going to be 1 and b is going to be 2. Those are our limits of integration, since we're looking for the area under this curve, but only between the x values of 1 and 2. We want to next know what is this function f of x. Well, this function is a line, as you can see. And if you recall, the equation of any line is given by y equals to mx plus b, where m is the slope and the b is the y-intercept. So what's our slope? To find a slope, we can take any 2 points on the line. So let's take these 2 points. Slope is rise over run. So the slope is -1 over 1, or just -1. And the y-intercept is where the line is going to cross the y-axis. So it crosses the y-axis at 4. So our y-intercept is going to be 0, 4, which means the equation of the line is going to be y equals to -1x, which is just -x plus 4. So get the slope, get the y-intercept, we have the line. But now we got to find the area of this blue shaded region. Well, the blue region, we can split this up into 2 different parts, a rectangle and the triangle right above it. So the area of a rectangle is given by the length times the width. So this rectangle has a length of 1 and a width of 2. So it's a 1 by 2 rectangle. So its area is 2. Now what about the triangle? The triangle is, so its base is 1 and its height is also 1. So the area is going to be 1/2 times base times height, which is just basically 1/2. So if we add these 2 areas together, 2 plus 1/2, it'll give you 2.5, and that'll represent the area of that shaded blue region, which is also this integral. So it's the integral from 1 to 2 of this line -x plus 4 dx. That's what this area 2.5, it represents. All right, now in this case, we want to find the integral from 0 to 10 of 2 plus f of x dx, where f of x is this given function, but we don't know anything about 2. Okay, so let's go and break this down. So first of all, we're taking this integral and we have a plus sign. So whenever we have a plus sign, we can split this up into 2 different integrals. We have the integral from 0 to 10 of 2 dx, and we have the integral from 0 to 10 of f of x dx, where f of x is given by this graph over here, but for the 2, we need to find the graph ourselves. Now, what does it mean to just have a 2 there? Well, 2, this is like saying we have the line y equals, remember, this is a function y equals to 2. So y equals to 2 is going to be a horizontal line. But we don't want the entire, anytime we have y equals to a number, it's going to be a horizontal line. We don't want the entire line, we just want the line between our limits of integration, which are 0 and 10. Now, as we can see, it's going to create a rectangle. Okay, this rectangle is going to have a length of 10 and the width of 2. It's going to be a 10 by 2 rectangle. So its area is going to be 2 times 10, which is 20. So when you have this line y equals 2, if you're looking at it geometrically, it's going to have a rectangle between 0 and 10, and the area is going to be right below it. That'll be 20. Now, what about for f of x dx? So from the beginning of this section, we learned that anytime the area is positive, we add it, and anytime the area is negative, so below the x-axis, we subtract it. So we're given that a1 is 7. Let me actually put these in. a1 is 7, a2 is 3, a3 is 2, and a4 is 1. But the ones that are below the x-axis, we're going to subtract. So we're going to have 7 minus 3 plus 2 minus 1, which is 5. And then the total area is going to be the area of the first region plus the area of the second region, and that'll be 20 plus 5, or 25. All right, now the last part is going to examine the limits of integration. So the first part, we have the area under f of x dx from 9 to 15, but we want to subtract off the area under f of x dx from 9 to 12. Okay, so let's see what that looks like visually, and we want to figure out what will be the new limits of integration if we subtract the second area from the first one. So f of x, it doesn't matter what the curve looks like, it's just going to be some curve. What we're really looking at is the limits of integration. So right now, the first one is the area under the curve between 9 and 15. So this is the area represented by this first term, 9 to 15. But we're subtracting off the area between 9 and 12. So imagine that second area gets subtracted off. So now we only have the area between 12 and 15 because we had the area from 9 to 15, but we subtracted 9 to 12. We took that off. So now we only have the area from 12 to 15. And so those will be our new limits of integration. A will be 12, B will be 15. Here's some rules of integration. If we have the area of f of x dx from a to a, it's equal to 0 because a to a just means it's the same point. So we have, like, we don't have an area, we're not going anywhere. So the area of this function between 2 and 2 is 0 because we haven't created an area. We haven't gone anywhere, we're staying at the same spot. And then the area of f of x dx from a to b is equal to negative the area from b to a of f of x dx. So for example, let's say that we're given the integral of from a to b of f of x dx is 5, then the integral from b to a f of x dx is negative 5 because we're just switching the limits of integration. All right, and then we have this integral from a to b of f of x dx, and it's equal to this following integral, and we want to find the bounds of integration. So I think the easiest way of doing this is to graph it. So we have negative 3 to 5 plus 5 to 7, but we're going to subtract off negative 3 to 0. Okay, so let's get a visual of this. We have negative 3 to 5, which is this first part, plus 5 to 7, which is that second part, but we're going to subtract off negative 3 to 0. So this is 0 right here. And we're going to subtract off negative 3 to 0. So then our limits of integration are, as you can see, are going to be between 0 and 7. All right, and then I think this is the last one. What is this following integral equal to? From negative 7 to negative 4. So if negative 7 to 0 is 12, negative 4 to 0 is 10.4. We just want to know negative 7 to negative 4. Best way is to graph this. So from negative 7 to 0 is equal to 12. And from -4 to 0 is equal to 10.4. We subtract those, and that'll give you 1.6.